Good morning, everybody. Science of Santa. This is usually a relatively short talk because it is allowed to give time to mulled wine, mince pies, anything else you happen to have going on. In this case, I was asked, can I make it just a few minutes longer by adding a little of explanation here and there? So I call this particular version of Science of Santa, the Director's Cut. So, I'm asking the question, is Santa compatible with the laws of physics? Or, if you want to make it a little more succinct, let's have a think about how many laws of physics Santa actually breaks. If you're ever asked the question from a youngster, is Santa real? Well, we don't want to lie to children, so I thought, can we actually come up with an answer that doesn't actually dismiss all of their beliefs? So how many laws of physics does he break? Let's remind ourselves that we all are, I'm sure, aware of the idea of Santa. He's allegedly a portly, jolly fellow with a white beard and a penchant for wearing red suits. Okay, that does display questionable fashion sense, but that doesn't mean that he can't exist. What about the claims that are made for this gentleman? It is said that he visits all households on Christmas Eve to deliver presents to all qualifying children. And how do children qualify? Well, it depends if they're on the naughty or the nice list, of course. So can we reconcile that statement about visiting all households on Christmas Eve? Can we reconcile these feats with our understanding of science, our understanding of how the world works and how the universe works? And when I first thought about this a few years ago, I thought, well, can I use any of the science that I've described in other outreach talks that I've given? I've given about maybe 40 or so different talks. Here's a small selection of them, talking about how the world works and in particular how the universe works, as astronomy is a great interest of mine. And so I thought, what can I use, what can I borrow from these various talks about how the universe works and see if we can apply it to our understanding of Santa. So let's take that statement once again. This is the statement that we're going to be analysing somewhat forensically. Santa visits households on Christmas Eve to deliver presents to children. Okay, let's start unpicking it one little bit at a time. Firstly, how many children does he actually deliver presents to? Okay, the Earth's population is about 8 billion. About 1/4 of those 8 billion are children, defining a child as up to 18, even though their biological age doesn't necessarily indicate their likelihood of getting presents from Santa. About 50% of these children are eligible for Christmas presents. I'm assuming that Santa is fairly generous and will deliver Christmas presents to children even if they're not in Christian households. That gives us an overall number of about 1 billion children getting Christmas presents each year. That does assume a certain ratio of naughty to nice, and just to keep the numbers nice and even, let's assume naughty is 0% and nice is 100%. I'm sure anybody in the audience with children or grandchildren will take issue with that particular ratio, but let's just keep it like that, just to keep the numbers nice and round. 1 billion children is what we're talking about. Okay, Santa visits households containing 1 billion children, perhaps a little less than 1 billion households. Let's not worry about little factors of 2 or 3 here or there. How does Santa visit all of these places? His transport, of course, is a sleigh pulled by flying reindeer. So we can ask the question, can reindeer fly? Well, we know that insects fly, and we know that birds fly, and we know that pterosaurs fly, though you don't see that many of them these days. And we know that even some mammals can fly. So the question is, do reindeer fly? Well, if reindeer can fly, they choose not to do so for a lot of the time because we see very few photographs or videos of flying reindeer. Just because there's very little evidence for flying reindeer, well, we have to be careful just because of a lack of evidence, because we have to remember the scientific mantra. Absence of evidence is not evidence of absence. So just because we can't find any photographs or any eyewitnesses who are sober saying that they've seen flying reindeer, that doesn't mean reindeer can't fly. So basically the jury is out. We cannot prove nor disprove that particular idea. Okay, how fast would he have to go in order to visit all the children in the world? Let's assume that they're spread around the world and he's got 36 hours to visit them all. 36 hours because he can use not only the 12 hours on average of night time, but also he can use the time zones of the Earth. If he does it in the right order, he can actually spread the night out to 36 hours or thereabouts. That means he would have to travel at something of order 2,000 kilometers per second. That sounds really fast, but we have to remember that is really slow. It is only 0.007 times the speed of light, written there as c. So he's not even close to breaking the speed limit. We know the physics speed limit. I give a series of talks that I call Fiat Lux, in other words, let there be light. In the first of the Fiat Lux talks I've given, I actually measure the speed of light as well as measuring the wavelength of light. And the speed of light comes out to be about 300,000 kilometers per second. So 2,000 kilometers per second of Santa, not a problem. He's moving at less than 1% of the speed of light. So we know that the only physics speed limit is the speed of light. Nothing can travel through space faster than light can travel through a vacuum. Bear in mind that because we live in an expanding universe, we do see galaxies moving away from us at incredible speed, and space can actually expand at any speed it wants to. Indeed, when we look at the most distant galaxies using either amateur telescopes or indeed things like the Hubble Space Telescope, we do see galaxies that are receding from us faster than the speed of light. That is not a problem. It's only motion through space that is limited by the speed limit of the speed of light. But Santa's nowhere near that anyway, so not a problem. But if you are moving really fast through the atmosphere, won't the sleigh get hot and won't we end up with roast reindeer? Just like when we see a meteor or an asteroid entering the Earth's atmosphere, a meteor is a streak of light because a tiny particle, perhaps a grain of sand or so, that sort of size, it gets hot. What's happening is the air in front of the object, when it's moving quickly through the Earth's atmosphere, the air gets compressed. It's not friction, which is what you tend to think of. If you think of an asteroid coming into the Earth's atmosphere, you might think that friction is making it hot, but no, it's actually the compression of the air in front of the object. Well, we know about this because I've given a talk on the ABC of stellar evolution, talking about how stars are born. And I'm not going to talk about the A and B, but the C of the ABC stands for compression produces heat. So when we look at stellar evolution, if we look at a large cloud of hydrogen, gravity pulls that cloud together, and as the cloud compresses, the cloud of hydrogen gets hotter, and it gets hot enough ultimately to ignite stars. So that is how stars are born, the compression of a large gas cloud. We also know on Earth, a much simpler example is if you pump up the air in a bicycle tire, the air and the pump and your hands get hot because of the compression of the air. So even if the sleigh is really aerodynamic, surely this is going to be a problem. Moving at really high speed through the Earth's atmosphere, won't the heat make the sleigh glow white hot? If we know compression produces heat, and we know that hot objects radiate light, so surely Santa and the sleigh and the reindeer ought to be easily visible. Now, if we are sitting around at a temperature of about 300 Kelvin, we're radiating infrared, but if we got much hotter, we would start radiating visible light. So you could say, right, if that's the case, surely the sleigh ought to be visible as a bright light in the sky. And you could say, well, maybe it was. Okay, it's pushing it a bit, I think, to claim that Santa's sleigh is actually the Star of Bethlehem. I think we've got the timeline slightly wrong if Santa was zooming around on Christmas Eve even before Christ was born. But in terms of bright lights in the sky, you could say, well, yes, we always see bright lights in the sky. People are always claiming to see UFOs. But of course they're spread all over the year, not simply on Christmas Eve, so that doesn't quite fit either. But there is another explanation as to why we don't see bright lights streaking across the sky every Christmas Eve. What sort of matter do we already know about that does not emit or absorb or reflect light? And light here means any electromagnetic waves of any frequency, any colour if you like. We already know about the existence of dark matter. Dark matter does not emit light. Even if you get dark matter hot, it would not emit light. Everything we know about all ordinary matter, no matter what it is, if you heat it up enough, it will glow. But dark matter doesn't behave that way. It doesn't emit light, it doesn't absorb light, it doesn't reflect light. So if Santa and his sleigh are made of dark matter, that would explain why he doesn't glow. It also explains why the sleigh does not show up on radar. Despite what NORAD might tell you, no, they're just lying to children. The sleigh doesn't show up on radar because, again, radar waves, radio waves, would not be reflected by the sleigh, and hence it wouldn't show up as a ping. In terms of an aside on dark matter, we have to remind ourselves that dark matter makes up something like 85% of all matter in the universe. Okay, we don't actually know what it is, that's just a statement of our ignorance. But if most of the universe is dark matter, then surely it's entirely reasonable that Santa is made of this stuff rather than the stuff that we see around us. We can't see dark matter, but we know it's there because of its gravitational effect it has on things that we can see. For instance, the way stars orbit in galaxies, or the way galaxies are bound together, or the way that matter bends light from distant objects, so-called gravitational lensing. All of these things are the influence of dark matter on things that we can see. And of course, trying to understand dark matter is still a very active area of research. We don't know what it is. We are looking for dark matter particles or trying to identify what material out there might be constituting dark matter. Okay, let's come back to our statement. Santa visits households. Okay, he visits households. How does he get into those households? How could he possibly get down so many chimneys? He would have to squeeze down thousands of chimneys each second in order to visit 1 billion children if he does them sequentially. And of course, we've already said that Santa is, at least allegedly, a rather portly fellow, and surely he would not fit down the average chimney, which might only be 10 or 20 centimetres or so in diameter. So how could he possibly fit? Well, there's no reason why, in principle, he could change himself in such a way that he could make himself smaller. We know that people, assuming for the moment that Santa isn't made of dark matter, let's just return to normal matter for the moment. If Santa was made like us of a collection of molecules, and molecules are made of atoms, and atoms are, well, what are atoms? Atoms are a nucleus surrounded by electrons. But what if Santa could change that? What if you replaced the atom, instead of being a nucleus surrounded by electrons, what if you replaced the electrons with muons? Muons are a heavier version of the electron, if you want to think of it that way. And if you were to replace the electrons with muons, well, the atom would be a lot smaller because the muons are heavier. And roughly speaking, the atoms would be about 200 times smaller. And therefore anything made of those atoms would be 200 times smaller. So instead of Santa being a gentleman a little more than 1.5 meters tall, Santa would end up being only a centimetre or so high. And he would fit down the chimney, no problem whatsoever. So that would not be an issue if he decided to swap all of his electrons with muons. Quite how he would do that, I don't know, but we're talking about possibilities here. And yes, you can make atoms smaller by swapping the particles over. Muons, we know muons exist. We do see them all the time. We see them especially as a result of cosmic rays hitting the Earth. And you can think of them as basically heavier cousins of the electrons. They have essentially all of the same properties, except that they are 200 times as massive. And hence an atom made from muons would be approximately 200 times smaller than a normal atom. So muons aren't fanciful, they do exist, we've seen them, we know they exist, but we simply don't know how to make atoms using muons rather than using electrons. Just because we don't know how doesn't mean you can't. Okay. That might work if you've got a chimney, but it doesn't help if a house or an apartment or a flat or whatever doesn't have a chimney. And of course, a lot of modern houses don't necessarily have chimneys. So in that case, how could Santa get inside? Well, again, quantum theory comes to our rescue, because we know it is possible to go from, for instance, outside a house to inside a house, even though there's no open door or open window. It's a phenomena that we know about called tunneling. An object can effectively tunnel through a solid object like a door or a wall or a window that isn't open, and starting on one side can appear on the other side. This is not simply theory as in conjecture or hypothesis, we've actually seen it happen. And we've built microscopes that are based on this principle. There is such a thing as a scanning tunneling microscope, and it's called a tunneling microscope because this is precisely what happens to objects within the microscope. They go from one point to another as if going through an object which is impenetrable. Now, quantum tunneling is one of those really weird results of quantum theory that goes completely against our ideas of common sense. But you have to remember that quantum theory has been around now for the best part of 100 years, and we've been continually testing it to try and make it break, to see if we can get any predictions that go against common sense and predictions that turn out to be wrong. But whenever we find a prediction from quantum theory which is against common sense, it turns out common sense is wrong and quantum theory is right. We have not found anything in the last 100 years that overturns that. We simply have to put common sense to one side. It's a bit of a shame. It means it's rather difficult to learn about quantum theory because your gut feeling is usually wrong when it comes to dealing with the results of what quantum theory is telling you. And in this particular context, quantum tunneling means that an object can move from point A to point B even if there is an impenetrable barrier between them. And in this context, I use the word impenetrable to mean, as far as Newton is concerned, as far as Newtonian mechanics or classical mechanics is concerned, Newton would have said it would be impossible to go from A to B because there's a barrier between them. Quantum theory says, no, it is still possible, even though you have what appears to be a completely impossible barrier to move through to get from A to B. So quantum tunneling is real, and we've built devices that work on that principle. So if that's the case, then in principle, Santa can go from outside a building to inside a building, even though the doors are closed and the windows are closed and there's no chimney. Okay, where are we up to? We've said Santa visits households on Christmas Eve. Okay, he does this in the 36 hours that he's allocated on Christmas Eve. He does this, quote, all in one night, unquote. Even if he's going really fast between each of the deliveries, and even if he can either go down the chimneys or tunnel through the walls, how does he manage to do this in 36 hours? Surely that's a big ask for anybody. Again, we can rely on our knowledge of how the universe works, not by looking out into the universe at the largest of scales, but again by asking, how do things behave on the smallest of scales? Excuse me. And we know, for instance, that particles can be in two places at the same time. So if a subatomic particle or an atom or a molecule, for instance, can be in two places at the same time, Why can't Santa be in two places at the same time? It's allowed by the laws of physics, so we shouldn't rule out that possibility. It sounds weird. It's one of these things that you think, well, that doesn't agree with common sense at all. If I've got a mug of tea, it's either over there or it's over there. It can't be in two places at the same time. But there's nothing in the laws of physics that say that can't happen. It's another of those weird results of quantum theory. One example of that is, for instance, if we think of an object spinning, think of an atom spinning or a molecule spinning, it can spin clockwise and anti-clockwise at the same time. Now, we think of the Earth spinning and it goes one way as seen from, for instance, above the North Pole. We don't imagine the Earth spinning both ways at the same time. It's completely against common sense, but that is because common sense is wrong. Not only can an object spin both ways at the same time, an object can be in more than one place at the same time. In principle, there's no limit to how many places. So if an object can be in two places, or three, or four, or five at the same time, why can't Santa be in more than one place at the same time? Why can't he be in two places, or 10, or 1,000, or 1,000,000? There is nothing explicitly in the laws of physics that would stop that. So maybe if Santa has to visit 1 billion places at once, maybe that's a lot easier if he can visit a lot of them at the same time. You might say, okay, I'm not quite sure about that. What if he can only be in one place at a time? Is there still any explanation as to how he can visit all of these places, potentially up to 1 billion households? How does he manage to travel to all of these places so quickly? There's another alternative to saying that Santa can be in more than one place at the time. And that is, we know when we look out into space that it is possible for matter to distort or warp space. It can also warp time as well, but let's leave time to one side just for the moment. If Santa was capable of manipulating space in the same way that matter distorts or warps space, then in principle, instead of having to visit all of these 1 billion households, Santa might have figured out a way of distorting space such that the actual distance from him to the various destinations gets shorter. So that instead of having to travel long distances to get from A to B, he effectively brings A and B closer together by reducing the space in between, by distorting or warping the space in between him and the various destinations. Again, we know that matter distorts space. We've seen it many, many times. Einstein's theory of gravity says that matter distorts the geometry of space. It's difficult to get your head around this because you can ask, well, what do you mean by the shape of space or the geometry of space? Or how can you talk about warping space if space is empty? If you think of space as nothing, it's rather tricky to figure out what's actually going on. If you think of space as a thing, then it's a little easier to think about how that could be warped or distorted. The bottom line is Einstein's theory works. General relativity works. The maths works. Even if it's tricky to visualize, the maths works. And the idea of changing the distance between objects is weird, yes, but as far as we can tell, it is the correct way to think about how the universe behaves. So if it's possible to do that, maybe Santa has figured out a way of doing that to his advantage to make it easier to visit all of these places. Okay, Santa visits households on Christmas Eve, and in doing so, he delivers the presents to children. Okay, so he gets around really fast. He covers the world. How does he take all the presents with him? How could he carry all of that? Let's assume one present for each of 1 billion children. It wouldn't make that much difference if it was 2 presents per child or 3 presents per child. How can the sleigh hold that many presents? The sleigh is presumably just a few meters long and a few meters wide and maybe a couple of meters high. So its volume is clearly only a number of cubic meters. That's clearly not enough for 1 billion presents. Well, yes, that's assuming that if we measure the sleigh on the outside to calculate its volume, then that gives us the volume inside the sleigh. But remember, it is possible for an object to be bigger on the inside than it is on the outside. We're back to this idea of it's possible to warp space in such a way that the idea of the volume inside an object and the volume we would calculate by looking at the outside, those would only agree if space is not warped or distorted. For instance, when we calculate what's going on inside a black hole, we can't actually look inside a black hole, but when we calculate what's going on, it looks like the volume inside a black hole is substantially larger than the volume outside a black hole. If we think of the event horizon as a sphere and measure the surface area to calculate its volume, the actual volume inside is much larger. Just for a second, let's think, if you don't like that idea, there is an alternative way of dealing with all the presents, and that is you just put them into another dimension. We are aware of 3 spatial dimensions: forward, backward, left, right, up, down. But it is thought that maybe there are more than 3 spatial dimensions, and it's just that we can only perceive 3 of them. We're not aware of the others. Some scientists believe that there are actually 10 or 11 or 12 dimensions of space. If that was the case, then although we can only perceive those 3, what would happen if Santa took one of the presents and moved it from our 3 dimensions into one of the other, the 4th, 5th, 6th, 7th, 8th dimension? It would appear to disappear from our 3-dimensional space, but it would still exist in the other dimension. So maybe Santa has simply moved the presents into one of these other dimensions, and then when he arrives at his destination, he pulls it back out of that dimension and puts it under the tree. Again, we don't know if that's the correct explanation because we don't know how many dimensions there are. We know that there are a minimum of 3, but maybe there are more. Maybe there are a lot more. But just temporarily returning to this idea of this weird result that it's possible for an object to be bigger on the inside than it is on the outside, well, you might think that's science fiction. I'm sure that you're all thinking of Doctor Who's TARDIS. Yes, bigger on the inside than the outside. That is a piece of science fiction, but that doesn't mean it is not also science fact. The familiar idea of geometry, for instance, taking the volume of a sphere or a cube by measuring the outside dimensions and calculating the volume inside, that only works if space inside is not distorted by matter. If you have matter existing, warping space, then the familiar concepts of geometry do not apply. And therefore it is possible to distort space to give you more space on the inside of the sleigh. It's still a bit of a push to talk about making it large enough for 1 billion presents, but the principle is sound. Okay, you might say, maybe these things are possible, but surely any of the things I've described, wouldn't that need a huge amount of energy to actually achieve? Santa and the sleigh and 1 billion presents moving at very high velocity, surely the amount of energy required would be off the scale. Well, yes, it would indeed need a huge amount of energy. But maybe Santa does have a huge amount of energy available to him. For instance, if a black hole can power a starship and take us to Alpha Centauri, why can't it power the sleigh? We haven't figured out the technology of how to do this, but a small black hole would provide enough power to send a spacecraft not simply to the planets, it could send a spacecraft to the stars, and we could explore the galaxy with a black hole powered starship. So if it's powerful enough to power a starship, why can't it be enough to power a sleigh? Now you might say, how do you get power out of a black hole? Surely that's a bit counterintuitive. Nothing can escape from a black hole. Nothing inside the event horizon can ever come outside the event horizon of a black hole. So how can we possibly extract energy from one? Well, it's true that nothing inside a black hole can come out. Anything inside is lost forever. But if you think of the region just outside the event horizon, the point of no return, if you want to think of it that way, then the region outside the event horizon can radiate energy. And if you harness that energy, then the black hole effectively becomes a power source. The energy radiating from black holes is called Hawking radiation because Hawking proposed it many years ago. It is at the moment still conjecture because we haven't been able to measure it in any meaningful way from a real black hole. But many scientists believe that although it's conjecture, it is sound physics, sound science. And there's an alternative. Even if you believe that it's not a black hole itself that's providing the energy, there is an energy source that we are overlooking. It's the elephant in the room, and that is what happens to all the mince pies. Now, many people leave a mince pie out for Santa. No one really believes that he eats them all. That would just be ridiculous. But what if, with all of the mince pies that are left out for Santa, what if Santa could convert the mass into energy? We know what the conversion rate is, E equals mc squared. So we can calculate what the energy equivalent of a mince pie is. So let's deal with how much energy and then think about how he would get the energy out. So first, how much energy is available in one mince pie? Well, in one mince pie, E equals mc squared, where m is the mass of a mince pie, 50 grams, and c squared is the speed of light squared. So in standard SI units, that gives us a total energy from one mince pie of 5 times 10 to the 15 joules. We'll come back to joules shortly. How many mince pies are left out? Well, we're not too sure. Let's assume a few % of households leave a mince pie for Santa, especially those households with perhaps younger children. Let's take a number of 20 million just to make the numbers nice and round. 20 million mince pies, 20 million multiplied by the number we've just calculated gives us a total energy available to Santa of 10 to the 23 joules. Now, even if you know what a joule is, trying to figure out what does 10 to the 23 joules look like in terms of how much energy is that, that's a difficult thing to get your head around. So one way of thinking of it is to imagine the energy output of a nuclear power station. If you think of Sizewell B or something like that, let's imagine we have a gigawatt nuclear power station. A gigawatt means it's generating 1 billion joules per second. Imagine that power station running every second of every day of every year for 1 million years. The total energy from that power station running for 1 million years would be approximately 10 to the power 23 joules. So you can see that if Santa can get the energy out of mince pies, he would have an absolutely enormous amount of energy to play with. And he has it, of course, over the course of one night. Okay, right, that's the amount of energy available. How would he go about doing that? How do you extract E equals mc squared from a mince pie? Well, there's at least a couple of ways you could do it that I can think of. The most efficient way of getting energy out of matter is to take whatever matter you've got and you take the antimatter equivalent and you collide them together. In this case, in the Large Mince Pie Collider at CERN, that would be a very efficient way of getting all the energy out of the mince pie. But you can see the catch with this particular argument. Yeah, where do you get the antimatter mince pies from to make the collision in the first place? Okay, so maybe that's not the way he actually does it. Is there an alternative way of getting energy out of a mince pie that doesn't involve the idea of an antimatter mince pie? Well, yes, you can extract a reasonable fraction, perhaps not most of, but a reasonable fraction of E equals mc squared from a mince pie. You could extract 10% or 20% of the energy of a mince pie by taking the matter and dropping it into a black hole. matter falling into a black hole, before the matter actually falls into the black hole, as it approaches the event horizon, the matter, part of the matter, a percentage of the matter, gets converted into energy and radiated away. We know this happens not from any experiments on mince pies, but we know that matter falling into a black hole, and a quasar is an example of a galaxy with a black hole at its centre. The matter falling into a quasar, okay, I agree, it's probably not a mince pie, it's probably gas and stars and things, but we know that when matter falls into a supermassive black hole, we know it's converted into radiation. The talk I give that's relevant to this I've called Ancient Light, because I've actually managed to photograph a quasar even without using a telescope. I photographed a quasar because it's producing so much energy you can photograph one of these objects even at enormous distances. How much energy could be released by dropping mince pies into a black hole? Surprisingly enough, I can't find any research papers on this topic. I can find very few examples of published studies that say this is how efficient the process is. But by looking at what's happening with quasars, we know that it can be very effective. Reminder that a quasar is simply the name we give for a galaxy with a nucleus that has a supermassive black hole at its centre, and a large percentage, at least 5, 10, 20% of the matter that's falling into the black hole, because of the extreme gravity around the black hole, a reasonably large percentage of the matter is converted to energy and then radiated away. And this is such an efficient process that light from a quasar can be detected even when the quasar is effectively on the other side of the observable universe. I've photographed a quasar without a telescope, even though the quasar was 25 billion light years away. That's such a ridiculous distance, and again, because of the expansion of the universe, this particular quasar that I photographed with my DSLR camera is actually receding from us at twice the speed of light. That is an indication of the distance of this object, and the fact that you don't need a telescope to photograph it is an indication of just how much light is being produced, how much energy is being produced by the matter falling into this black hole. So again, we're not quite sure what would happen with mince pies, but if it's that efficient with large black holes and stars, surely it must work for mince pies as well. Okay, maybe he can do all that, but how does he know how to manipulate space and time? How does he know how to use quantum mechanics to his advantage to get him to visit all of these households to deliver the presents to children? If he does want to bring the households to him by manipulating space and time, how does he manage to do that? Well, one thing we have to remember is, well, who says he has to be human? Maybe he has some skills that we're not fully aware of. Remember, children are asleep when Santa visits, so we don't actually know what he looks like. We just assume he's a jolly fellow with a white beard and a penchant for wearing red suits, but maybe he looks a little different than the classic Christmas cards would have us believe. So returning to the original question, is Santa compatible with the laws of physics as we understand them? Just how many laws of physics does Santa actually break? I would argue that the answer is none. You have to bend the rules a little bit, but he doesn't actually break any laws of physics. So feel free to draw your own conclusions about the existence, or otherwise, of the portly, jolly fellow with the white beard and a penchant for wearing red suits. And regardless of the conclusion that you come to, well, may I wish you all a very Merry Christmas. Thank you for listening.
Right.